Okay, I'm really excited about this chapter because what it allows us to do is take the equations that we were working with in last chapter, like 2x plus 3y equals 6, 4x plus 5y equals 7, organize those numbers into matrices, and be able to solve with the use of our calculator. But of course, before we can do that, we need to know what is a matrix, how do you work with it, and just what can you do with it. So that's where we start. What is a matrix? Matrices, which is the plural name for matrix, is just a rectangular array of numbers written within brackets. If you look at the matrix here, this would be matrix A. It has 2 rows and 3 columns. It's important to note that the rows are across, columns go up and down, and then we label a matrix using those 2 pieces. And we always start with the rows and end with the columns. This is really important to remember because if you need to remember the rows by columns so you know how to enter it into your calculator, how to work with it. That's why my intention is to bring an RC Cola today. We'll see if I did tomorrow. But it's to get you to realize, not to taste nice delicious pop, but to realize that we label them rows by columns. So let's go ahead and let's start with example 1. Example 1 is a matrix. Can you label the dimensions? Hopefully you see that there are 2 rows and 2 columns. So the dimensions of this would be a 2 by 2 matrix. The second one has 1 row and 3 columns. So we would name that, or we would label that as a 1 by 3 matrix. 1 row, 3 columns. Now after you know how the dimensions work, it's easy to identify the specific element in the column, or element in the matrix. So given example 2, this is supposed to be a capital K, by the way. If matrix K is equal to this matrix, identify the element that corresponds with what's given. Well, the first number corresponds to the row, so this would be row 1. The second number responds to the column, or correlates with the column. So this would be column 2. So we're identifying which element is in row 1, column 2. So we go to row 1, column 2, and see which element matches, and that would be -1. So K12 is equal to a -1. Notice how we have a little k, that's how we know that we're identifying an element, whereas a capital K is what identifies the matrix. Okay, letter B. This would correlate with row 3, column 2. So I go to row 3, column 2, and that element would equal -4. Try C and D, and then we'll check up here on the screen. Go ahead and check to see, did you have K23 equal to 4 and K34 equal to -5? All right, let's go ahead and flip it over. Now, how is this helpful for real-world applications? Matrices are beautiful. In fact, they're used quite frequently in businesses because it's a quick way to organize information, to look at patterns in data, and be able to multiply or add numbers depending on the scenario. So here, we have many uses in real life. One application would be to use matrices to represent a large amount of data in a concise manner so that we can process the data in various ways more conveniently. For example, the sales of different types of pre-packaged food from 3 stalls during a given period of time could be shown in the form of a table here. Stall A sells 36 packs of noodles and 27 packs of rice. Stall B sells 21 packs of noodles and 56 packs of rice. And stall C, 43 noodles and 35 packs of rice. How can we represent this in a matrix? Well, just take those numbers and organize them into an array, a rectangular array of elements. So I would have 36, 21, 43, 27, 56, 35. and this would correlate with stall A, B, and C, and this would correlate with packs of noodles, and rice sold. Okay, how could I have done that differently? How could I take that rectangular array and make it into a different matrix? Well, right now, this would be seen as a 2 by 3 matrix. We can change this around and make it into a 3 by 2 matrix. We just have to make sure we label what the numbers correlate to. So if I instead call this stall A, and this one B, and this one C, and this packs of noodles, and this packs of rice, I can organize this information differently. So in stall A, packs of noodles would be 36, rice sold would be 27, B, noodles would be 21, rice would be 56, C would be 43, and 35. Essentially, we've taken this matrix and just kind of flipped it around. So there's different ways you can organize the information. That way, let's say that we're looking, well, stall A sold noodles and rice for $10 a pack. B sold it for $10.50 a pack, and C sold it for $9.50 a pack. Well, then we could multiply by the price, and we'll look at matrix multiplication later, and determine what the profit was for each stall. So we will take a look at that later, but just to know that's coming. Right now it's how do you set up those matrices. Okay, moving into 4.2 then. After you know how to set up a matrix and how to label its dimensions, you have to know, well, what can we do with different matrices? And one of the basic operations we can do, if the matrices have the same dimensions, is we can add the corresponding elements. So in matrix A, element A corresponds with row 1, column 1. I can add it to element R, which also corresponds to row 1, column 1 in matrix B, and I'll have the sum in that first row, first column of a new matrix. So let's go ahead and and then you would follow along with the other elements. So let's try this with example 4. Example 4. If I am adding, well, first of all, this matrix would be a 2 by 3. This matrix would be a 2 by 3. If I add the corresponding elements, in row 1, column 1, I'm going to add 1 plus 3 to give me an element of 4. Negative 2 plus 9 to give me an element of 7. 0 plus negative 3. 0 plus negative 3. Then 3 plus negative 9. Negative 5 plus 6. And 7 plus 12. And I can go ahead and write my new 2 by 3 matrix, which is 4, 7, negative 3, negative 6, 1, and 19. Okay, you don't have to show this middle step. I was just showing you which elements we're adding together. Go ahead and do that for the next matrix and check it up here at the screen. Okay, go ahead and check your sums and see if they match. Okay, what properties can we use with matrices? Well, matrices are closed under addition, meaning if you have an n by n matrix and you add it to the same dimensions, just like we did above, you're going to end with the same dimension matrix. Commutative property works on matrices, where you can switch the order of how you add matrices. Associative property works. There's an additive identity property where we can add a 0 matrix plus a matrix and get the matrix back. There's an additive inverse property as well, and this is all working with just addition, where we can add the opposite of a matrix and get 0. And these two properties are important for working with equations. So let's move to the next piece and see Well, how does the additive identity property work and the inverse? This is the identity. This is the zero matrix. This is an example of the additive identity because we're adding one matrix to a zero matrix, and we'll find that we get the same matrix back. The matrix maintains its identity. 9 plus 0 is 9, 0 plus 0 is 0, negative 4 plus 0 is negative 4, 6 plus 0 is 6. Yep, the same matrix we got back. And this is an example of the additive inverse. Inverse is another name for opposite. We're adding the opposite matrix, and let's see what we get. 3 plus negative 3 is 0, negative 8 plus 8 is 0, negative 5 plus 5 is 0, and 1 plus negative 1 is 0. We got back the identity, the additive identity matrix. Okay, let's try example 5. Let's take a look at matrices closed under subtraction, and then we'll use it in an equation. So here's an example of the closure property. Closure property, saying that if I subtract A minus B, I'll get the same dimensions back. So 2 by 2 minus a 2 by 2 is going to give me a 2 by 2 matrix. So I take row 1, column 1, element 4, minus row 1, column 1, element 7. That'll give me the first element. 8 minus negative 9 will give me the second element. Negative 2 minus negative 4, minus 4. And then 0 minus 5. So my matrix will be a 2 by 2 that will exist of elements negative 3, 17, negative 6, and negative 5. So there's an example of the closure property. And now we can use that closure property to identify missing elements. If we know that a 2 by 2 matrix plus a 2 by 2 matrix will equal a 2 by 2 matrix, we can figure out what those elements, those missing elements, are. So we can go ahead and we can add is equal to x, y, 0, z, and we would have 3 plus negative 2 give me the first element, negative 8 plus 6, negative 5 plus 5, and 1 plus negative 2. And now I can go ahead and use these for my variables. X is 3 plus negative 2. So my x variable, 3 plus negative 2 is 1. Y is negative 8 plus 6, which is negative 2. Negative 5 plus 5 does equal 0, but I don't need to say that. We know that's true. And then z is equal to 1 plus negative 2, which is negative 1. So there's my answers for x, y, and z. Alright, so let's go ahead and flip it over and see, well, how do you solve an equation with matrices since we have these properties available? And that brings us to 4.2b. Solve the matrix equation for x. So if I have x minus a matrix is equal to another matrix, since these matrices have the same dimensions, I know that when I use the additive inverse, I add the opposite of this matrix, I will have another matrix that is also a 3 by 2 matrix. So I'm going to add the numbers in these matrix. So I'm going to add 2, 5, 3, negative 1, 8, and 0. 2, 5, 3, negative 1, 8, and 0. And if I look at this piece, I have negative 2 plus 2 gives me 0. Negative 5 plus 5 is 0. Negative 3 plus 3 is 0. 0, 0, 0 is equal to, and now I'm going to add these, so I have x minus 0 is equal to 10 plus 2 is 12. Negative 3 plus 5 is 2. Negative 4 plus 3 is negative 1. 9 plus negative 1 is 8. 6 plus 8 is 14. Negative 9 plus 0 is negative 9. Now, we looked how any matrix, if you add or subtract it to the zero matrix, gives you the same matrix back. So x, matrix x, would equal these elements, 12, 2, negative 1, 8, 14, and negative 9. And the beautiful thing about this is it's an equation. We can go ahead and check it. If I plug this back in for x, I can just subtract the corresponding elements. 12 minus 2 is 10, 2 minus 5 is negative 3, negative 1 minus 3 is negative 4, 8 minus negative 1 is 9, 14 minus 8 is 6, and negative 9 minus 0 is negative 9. So I know I have it. All right, example 2, we can use the closure property to go ahead and solve for missing variables. So since I have a 2 by 2 matrix equal to a 2 by 2 matrix, I know their corresponding elements are equal. So 2m minus n has to equal 15. Negative 3 has to equal m plus n. 8 equals 8, I don't need to write that, and negative 30 equals negative 30. Okay, how does this look similar to the last chapter? Well, we have two variables, so what could I do to solve? You can either line these up and use elimination. Many people prefer that, so I'll go ahead and line this up as m plus n equals negative 3. And then I can add and eliminate to solve. 2m plus m is 3m. Negative n plus n is 0. 15 plus negative 3 is 12. So m is equal to 4. What can I do after I solve for m? Plug it into either equation and solve for n. So I have negative 3 equals 4 plus n. Subtract 4 from both sides. And I see negative 7 is equal to n. Okay, we're going to stop there. Tomorrow we're going to start on matrix multiplication. And we're going to really start seeing the value of matrices in the next upcoming week.